Okay. All right. So, yeah, it's 10:06, so close enough. So I'm gonna get started. This is welcome back to Introduction to Software Engineering. I usually like to start the classes by looking at the calendar and seeing what's due this week. There's nothing due this week. Um, sorry, one sec. My voice is almost gone. Um, there's nothing due this week. There is stuff due next week. Nothing, the specs have not been released yet. I expect to release them either later today if I don't get distracted by other stuff. And if not today, then early tomorrow. All right, so they're basically done. I just have to double check, look for, find all the mistakes so that you guys don't have to find them for me. I will show you a little bit of the submission server, which is where you'll be submitting your tutorials. Okay, so if you go, the submission server is up. So there is an IP address listed on Brightspace in the tutorials section. And if you click on it, it should bring you here. If you're on campus, you will not have any trouble whatsoever. If you're off campus, you will have to start up your VPN before you do it, right? So I'm not sure, I mentioned that if you use OpenStack, you might need the VPN, but that the actual truth is that you will need the VPN if you plan on submitting a tutorial from anywhere other than the campus, right? So you cannot connect to this unless you're on the VPN or on campus, right? So hopefully that's clear. So you will need a VPN for this class. Zoom in, sure. Okay, so how the submission server works is, well, there's not, I mean, I'm not allowed to connect to Brightspace, so I can't use like the single sign-on from the school. So the security works as follows. You get a secret code, which is basically your student number and maybe your email, I forget. A bunch of stuff hashed together into a string that is statistically going to be unique, right? If there's a duplicate string, then we've broken encryption. So, but what you're going to do is you're going to put your student number in, say email me my secret code. I have a class list on the server. If you get something like student number not found, please contact me, right? That means if you've registered late, that could happen, right? I have to manually update this class list, and which I will do a couple times over the next few days. But if you happen to miss that window, then please contact me and I will make sure that I update it. So you put your student number in here, email me my secret code, check your Carleton email. There'll be an email with a secret code, and that secret code is your key to doing anything. So in my case, I have, well, tutorial 1 is up. So I click here. It's going to take me to this page. I can still get my secret code if I want. I mean, it's not, there's no limit on the number of times you can get your secret code. You can get it every time if you want. You do not have to remember it or store it anywhere. But here's the tutorial 1 instructions. There's just a few things. Right, you're limited to 1 submission every 5 minutes. That is to make sure the server doesn't get overwhelmed. So these will time out, right? Because, you know, sometimes people put in infinite loops or other things that can really mess stuff up. So there's a time limit for your code. And if it's busy, your code could actually run for a long time, a lot longer than it should, right? I'm working on that, but it's not simple. No, the secret code is always the same. Okay, so yeah, you can reuse this, just reuse the same secret code. But, right, if you don't have to go searching through your email, you can always just ask for, please send it to me again. It's not a problem.
I have so many freaking friends, bro. What the heck? I'm not social
All right,
enough.
all right, all right. If you have any questions, please let me know. Oops. All right, so let's say that I wanted to submit something for this tutorial. I can choose my file. So here I have tutorial one solution. I also have to enter my secret code, which is, for me, I get the nice convenient one. Upload the tutorial, you're going to see a message and then some output. If the server is busy, this might pause here for a while, right? As other people's stuff gets run. So you can always navigate away. This will also be emailed to you, right? So every time you run it, you can wait here and see the output. So I got 16 out of 16. But if it's taking too long, you can just navigate away, do something else, and check your email later. You get the best grade. So let's take a look at that. Now the UI is, not only is it terrible, it's probably like frustrating because, well, whatever, I don't know. So you're gonna have to use the back button for your browser for a lot of places. But then once I go back to my assignments, I can take a look at my grades. So again, I'm gonna use my secret code. Choose tutorial one. The latest one should be at the top. Yeah, that looks right. So this is the latest one. I got 16 out of 16, but out of all of these, it will store 10 or 11, right? So depending on what the last thing you call, anyway, there'll be 10 or 11. The rest get deleted as they sort of age out. And out of these, the highest will be the grade that you get. Okay, so if you have a 16 already, well, then you're done. Yeah, I miss Gradescope too. Gradescope was was fantastic. It was just very expensive, apparently. Yes, I'm right there with you. In fact, the only reason this server exists is because they told me at the last minute, right? So I was teaching a summer class that started in May, and like April 30th, they're like, "Oh yeah, also you can't use Gradescope." And so like I built this in a week, which is why like the UI is kind of rough. You can also view your files, not all of them, right? So this is a test file that I use, and this is your results, but you might, test.cc is something that I uploaded there so that to test your code, so you can kind of see what I'm doing behind the scenes. But this will help you to make sure that your code is packaged correctly, right? And at the very least, you can check to see that it's not an empty folder, right? So you can, if you click view files, you can make sure that you didn't do something like submit an empty folder or submit the starter code or something like that. So you can rule out some basic mistakes that way. I put this up. Oh, geez. This is what happens when you like build this in a week. I put this up and there was like a huge security flaw in it, right? A student was nice enough to inform me and I had to take it down. And then I fixed it. I'm pretty sure I fixed it. But if I happen to notice a security flaw, I might have to take away this feature again. So, or if you notice a security flaw, please tell me. I don't know. Like, yes, you can wreck the server, but that is certainly an academic violation. You are not really allowed to mess with other people's submissions or even see them for that matter. All right. Questions? If you have any questions, feel free to email me. Again, it's a little rough around the edges, but I think it'll work fine. Okay. Last class, we were yeah, all right. Last class, we were talking about compilation of a program. So typically how you would organize your code, right? So we saw the, I'm just gonna, oh, whoops. Sorry. Give me 1 second. So I just taught the other class, so I'm not quite, I have to sort of transition into this, what is it? We are C, right? Oh. Okay. All right. So I'm using Windows subsystem for Linux. I'm a different section. Would I be able to get the WooClap attendance this week? Just have conflict? Yeah. Yep. That's fine. If you happen to attend a different section. Now, I don't imagine this room will fill up, but I'm guessing this is the most popular section because it's not at 8:30. But if it does fill up, then I'll have to like not allow other people from other sections to sit in. But as long as it doesn't fill up, I'm kind of fine with it, right? Like just do whatever. You can sit in and participate in this WooClap. There will be no WooClap today, unfortunately. I should have made one. I didn't realize that I didn't have one for these set of slides. I thought I did, but it's actually comes after comes after the next two sets of slides. No tutorials this week, right? No tutorials, no office hours, nothing is due. We're still getting set up. I will release some stuff that you can get started on early if you prefer. There's not even really OpenStack, right? It's not ready yet. They're still setting that up. All right, so today I'm using Windows subsystem for Linux, which is just basically a command line that is running the Linux operating system in your Windows operating system. So it's kind of nice here. And you can connect to it the same way, right? If I go down to my my sort of SSH connection, so this little thing down here is for that SSH connection extension, but I can also connect to WSL. So this Windows subsystem for Linux, it finds it, it connects to it, and then I can just modify my programs in here and run them in here. And that's how mainly I will be doing it. It's what I find the most convenient from Windows thing to do. So last class, so we don't need that right now. Last class, we had something that looked like this. I forget exactly where we left off because I am running 3 sections of this. It's so some of this stuff might be a bit repetitive. But we made a Hello World program. We compiled it. We ran it. We got Hello World. And then the next step is we wanted to do something a little more complicated, right? So we wanted to, we put a second function. We put foo, I believe. Anybody remember exactly how far we got? I looked it up this morning and now I can't remember.
We did not get to full.
We didn't get to foo, so we didn't get to this part?
No,
All
no.
right, perfect. Thank you. All right. Okay, so what happens when I want to make a more complicated program is typically one of the things I'm going to do is add more functions. And so I want to call this foo function from my main function. And so I'm going to compile it. I'm going to run it. And there we go. So now I have, I'm starting to build something with a little more complexity. But I don't like the way this is organized. I like to keep my main function at the top because I find it easier to read. So I'm going to put foo down here. And then I'm going to compile. And our compiler complains. And our compiler complains because our compiler is dumb, right? It's naive, which is kind of a good thing. It doesn't do clever things for us, but we can make it do clever things. But one thing it does is when I compile a file, it just starts reading from the top. and it reads from top to bottom. It does not do like 2 passes. It just does 1 pass, which means that it reads this. It says, okay, I'll import the IOStream library. I will scope in the standard namespace. I can print this out. I know how all this works. But this, I've never seen this before, right? This is completely new to me. I don't know what you're doing here. This looks like it might be a function, but I've never seen a foo function before. And so it crashes right there, stops compiling. Meanwhile, the foo function source code is down here. So what I need to do is tell the compiler, like, hey, trust me, there is a foo function. Here's what it looks like, right? So now you can verify that I'm calling it correctly. I'm not giving you the source code yet, but I promise to give it to you later. So if I tell the compiler about that, it gets to here, it says, okay, here's that foo function you told me about. I can see that you've used it correctly. I trust that you're going to give me the source code later. And then when it keeps reading, it finds the source code and it's happy. And we get an executable. Okay, so good. So if we want to move our functions around, we can always tell the compiler about them to say like, hey, I'm going to give you the source code later. But before I give you the source code, I'm probably going to use this thing. So here's the definition. All right. So we want to put foo now in a separate file. So one of the things that happens in C++ is that compilation can take a long time. For us, it's not going to, right? You can compile from scratch all of our assignments, and it might take like 1 or 2 seconds at the most. So it's not going to be a problem, but you get 100,000 lines of code, that can be a big problem. So we want to separate our code into separate files and compile them separately. And then what we want to do is called the linking. So we're going to compile them separately, link them together into an executable. And the advantage there is that if I make a change to one file, I just have to recompile that file. And then I can relink it to the executable. All right, so let's start doing that. We're going to put foo.cc here. And then I'm going to copy this foo function over. Now, before I link, I'm going to show you the wrong way to do this, okay? But this works. It just demonstrates, sort of how the compiler works. So I'm just going to include foo.cc here. Now, what this does is now when I compile, well, it still works. Still works. It compiles just fine, but what it's doing is, again, it's compiling both of these files at the same time. So the compiler starts reading here, bring that library in, great. Scope in the namespace, include foo.cc, okay. It just jumps over here and keeps reading. It's remembered all the context. It remembers everything that it already read, right? So that means it knows about the input-output stream library, and it knows that the standard namespace is scoped in. So in some sense, it's as if I just copied and pasted that code right here, which is fine. That already works. We know that works. The problem is that, of course, now we're still compiling both of these files together. Every time I make a change and I recompile, both of them get compiled. And I want to compile them separately. So instead of include, right, this is the wrong way to do it. The right way is to say, hey, there's a function called foo. I'm not going to give you the source code yet, but here's what it looks like so that you can verify I'm using it correctly. Then when the compiler sees this, it says, oh yeah, there's foo. But it doesn't have the source code, which means that I can compile this into machine language, but I can't compile it into an executable because it's incomplete, right? So there's going to be, right, if I compile this and I look at the assembly language, there's going to be a jump instruction here, and there's going to be some memory location, but that's going to be blank, right? The memory location is going to be where foo exists in RAM or virtual RAM, but that won't get filled in until the linking step. So what that means is that I can still compile main, but I can't compile it into an executable. I have to compile it into an object file. So C stands for object dash C. You can see the output is main.o. It is machine language, but so it's essentially nearly the same as this, but it's missing the foo function. And it's also like there's a flag saying it's not executable, right? So if you try and execute it, it's not going to work. All right, so I have main compiled, and now I want to compile foo separately. So let's try the same thing with foo. All right, so the compiler is very confused here because before when I compiled foo, again, it had the context, right? So when I said include foo.cc, by the time the compiler got there, it had already read these lines. And so it had this necessary context, but now I'm compiling it separately, it doesn't. So I have to add that context to this file so that it compiles correctly, right? So I need the input-output stream library, and I'm lazy, so I'm going to scope this standard namespace in, and then the compiler should be able to compile this. All right, so now we have foo.o and main.o, and those are both fully compiled. The only thing that's missing is, of course, in main.o, there is a jump instruction here that does not have a memory location. So the linking step is going to fill in those memory locations. That's kind of fast, right? Doesn't take very long to do that. All right. Questions so far? Okay. So the last step, I want an output file. I'm going to call it main, and I want to include this object file and this object file. And there we go. Hello world, hello from foo. Now, the nice thing is these are compiled separately. And in fact, if I, for instance, made some changes to this file, okay, let's recompile foo. I'm not going to recompile main though, because main is fine. Right? Nothing has changed here. I'm still calling the foo function. The foo function is different. So in order to change the, to make sure that's in the executable, I'm going to relink it. But I don't have to recompile main.o. So there we go. Okay, so that's basic program structure. Your tutorial 1 is on this essentially. We're going to look at it a little more. We're going to look at Makefiles and stuff. And test 1 is going to include, like, you will have to write your own Makefile. Ideally, again, I still don't know exactly what's happening. I have to talk to the COMAS people. But if everything goes the way I would like it to, then you will have to make a nice, simple Makefile, which we're going to do next. And to make a Makefile, you need to know Makefile, how to make it, of course. But you also have to know all of this stuff, like how your different, basically, files are compiled into object files and then linked together. So you should know all these commands. But also, though, if we do write the COMAS test, I'm going to be, because I know how it can be when you're programming and you just can't think of the thing that you knew 5 minutes ago. So you're going to be able to ask TAs questions, all right? So don't panic that you have to memorize this exactly. You can ask for like hints and stuff. All right, questions? Okay, so so this is where we were started from. We had some C++ source code, maybe a couple files, but we just include them all together and we build them, we compile them all at once, and then we get our executable. But that's sort of the inefficient way to do it. It works. But what we prefer as programs get bigger is we break them into pieces. And basically those pieces are called translation units. And they sort of correspond to, each file gets its own translation unit. Each file, there's a one-to-one correspondence of object code to source code. files. All right. Once we have all the object code, we link them together and then we run it. So program building is at a high level, translating source code into machine code, right? Whether we use linking steps or not, that's all that it is. So source code is instructions written in a high level language resembling English, can't be understood by your CPU. The machine code is basically instructions that get sent straight to your CPU, right? There's no interpreter there. There's no virtual machine. There's no JVM, right? So that's one of the reasons why C++ runs quickly, is because it compiles into instructions that your CPU understands. In general, executables are not portable. And now you might think, well, they all run on the same hardware, right? And these are CPU instructions. If I have the same CPU, why wouldn't it run, right? So this computer here has a Linux partition and a Windows partition. And so I can take the same program, I can take a program, I can compile it on Linux. If I move to Windows, I can't run it, even though the hardware is exactly the same, because in addition to sending things to the hardware, we're also making operating system calls, right? If we ask for memory, we ask the operating system, and Windows handles that differently from Linux. So they are not compatible because of that, even though it's the same hardware. So if I compile something on Linux, it will not run on Windows and vice versa. And that includes Mac as well. Although, well, I would have to test that to be 100% sure. It's Unix compliant, eh? So there might be some edge cases there. Typical executable contains code from many sources. So your code, other people's code, libraries. Every single executable has exactly one main function, right? So that's what makes it, allows it to run. You cannot have more than one, and you cannot have less than one. Object code, you can have less than one if you like. All right. Yeah, I think I talked about all of this. So now, when we compile and build our programs, it's going to look something like this. We're going to make a bunch of separate C++ source files. Generally speaking, each one of these will correspond to one class. And then each of those we will compile separately into object code. And then we are going to take all of those and then probably some outside libraries like the input-output stream library, and we're going to link them together into an executable. Now, linking is fast compared to compiling. So the more linking we do and the less compiling, sort of the better. Once we've done that, we have a program that will run. All right, so this is some of the syntax of how we do that. If you forget, right? So this, I can take a source file and compile it straight into an executable. Or I can take a source file and compile it into an object file, and then I can link it to itself, basically, into an executable. Or I can do that with multiple files, right? So I can make two object files and link both of those into an executable. Goodness. All right, this can get complicated quickly. So to help keep it right, we have two files. We have foo.cc and main.cc, and we need 3 compilation instructions for those 2 files. And so you can imagine if we had 20 files, now it becomes a real pain. So what we do is we use what are called Makefiles. It's a build tool to help keep the process organized. Now, Makefiles may seem kind of I don't know. They might seem like they're doing a lot, but they're really not. And in fact, you don't even need a Makefile. You just need a shell script, or you can write a C program that'll compile your stuff for you. Right? So there's nothing special about a Makefile. It does some cool stuff like manage dependencies, as we will see. But at the end of the day, it's really just a script. All right. So as we make files, we'll get, actually, let's look at the example and then we'll talk about that. Sorry for the coughing. All right, so Makefile, I like to do it with a capital M. I believe a small m will work even on Linux, but it might depend on what version of the compiler you're using. As always, test this stuff out, please. I say a lot of stuff and then I try it out and I'm like, oh, it's a change now, right? So as the compiler changes, sometimes these rules change. I use a capital M. And so now we're going to take those instructions and we're just going to put them in the Makefile, but we're going to give a command that's associated with each one, right? So for instance, one of my commands is main.o. This is the command that's going to generate my main.o file. I'm going to put a colon here, and now I'm going to list the dependencies. So a dependency is, well, in this case, it's main.cc. And what I'm saying is, if main.cc has changed since the last time I ran this command, then please run it again, right? So this is a dependency. If main.cc changes, I have to recompile this. After the dependencies, I list the command. So I have to do a tab over. If you get, generally this works pretty well, but if you have spaces instead of tabs, I think it's confusing to the Makefile. It's one of those things, I don't remember all the details of it. But there are errors where if your IDE replaces all your tabs with spaces. Now, if you're using VS Code and you install like the Makefile extension, that's generally not going to happen. But it can happen if you're like, say, downloading a file from some other, let's say, OpenStack. It can do a bunch of conversions as it does that. So do be careful with that stuff. But yeah, -c main.cc. So this is the command that's going to generate main.o. This command is called if main.cc has been modified. Same thing for foo. Foo.o depends on foo.cc. If foo.cc has been changed, I want to recompile it. And the command to do that is g++ -c foo.cc. All right, so now I have my two object files. I want to be able to link them. Well, this is going to be my main command. Right, I want to generate the main executable. The dependencies are main.o and foo.o. So if either of these things have changed since the last time I compiled this, I need to recompile it. And the command is this. All right, so now I have a Makefile to help me automate this stuff. I'm going to remove all the object files and remove main. And so now I just have the source code and my Makefile. And I'm going to run make. Undefined reference to main. Sweet. What did I do?
-o main.
Oh, yeah, I see. I didn't give it a name. All right. All right, well, let's see it in all its glory. All right, there we go. So those are the three instructions that I gave it. So the first thing it checks is main. It says, well, it depends on these two commands. And do I need to recompile these files? Well, it can't find those files. So it says yes. So the first thing it does is it recompiles main.o, and that's the command. And then it recompiles foo.o, and that's the command. And then it links them together. Right, so the nice thing about the Makefiles is that it tracks these dependencies. If you do your dependencies correctly, then if I make a change to one file, it does not recompile everything. So for example, let's say I changed foo.cc. Now when I run make, well, it says, it looks at the make file and says, foo.cc has been changed since the last time I compiled this. So I have to recompile this. And if I recompile this, well, this is a dependency of main, so I have to rerun this one as well. And but it does not have to rerun this command. So it only reruns these two commands, recompiles foo.cc and links them together. All right, questions? Okay, so this works much better in theory than in practice. In practice, it is easy to miss a dependency. It is easy to not realize you're missing a dependency. Also, when we're dealing with virtual machines, sometimes, right, I might be running VS Code, and VS Code has one idea of what the time is, whereas on my virtual machine, the time is something different. So you might get like a message saying you're trying to compile this file that exists in the future. Yes, I'll talk about that as well. Yeah, so the .h files. But so what happens is that if you very carefully maintain the dependencies and all of the clocks on all of the machines that you're using, then in theory, it should work out perfectly. In practice, if you fix a bug and you run make and you run it again and the bug is still there and you're pretty sure that it should have been fixed, then try to wipe everything clean and compile from scratch. So that's the next thing that we will do, and then I'll show you sort of a header file as well. So in the instance that I want to clean everything, generally speaking, we include a clean command. Now, there are no dependencies from this because every time I run the clean command, I want it to run, right? So I don't include any dependencies. I just put the command and I'm going to erase this executable and all of the object files. So all the compiled code gets wiped clean, and then I can rerun it from scratch. So I can run make clean, and you can see here all of my object code and executables are gone, and then I can run make, and that's usually a good idea. And in fact, I would kind of recommend always running a clean step before recompiling, simply because you don't want to be fixing a bug and then somehow being tricked into thinking you didn't fix the bug. That sucks when that happens. It's happened to me and it's happened to other students. So, and these programs we're building are not that big. So I'd recommend cleaning it every single time and recompiling from scratch. It's just going to take a couple seconds and it might save you some huge headaches down the road. Okay. One last thing before we talk about header files. Generally speaking, your make file has a clean command. That's a good sort of rule of thumb. But also you might have an all command. So in this case, I'm only making one executable. It's the main executable. But there are often times where I want to generate multiple executables in the same make file. And so I would just sort of list them all here, right, if there were more than one. And then when I run make, well, make always finds the first command and runs it. And so if you have all at the top, it'll look at all and then say, oh, I need to generate these 3 executables. And so it'll go ahead and do all that for you. So good form to, you make your make file that generates your executable, but it's good form to also include an all command and a clean command. Does the order of the make file matter? No, except for, of course, whatever's at the top is the thing that gets executed. If I just run make. So that matters. I believe these are actually interchangeable. You know what? Let's try it out. That's a good question. So the question is, does it matter if I do something like this? Well, let's run a clean and then a make. So no, generally speaking, there might be like, again, like I don't know every single thing there is to know about Makefiles, so there might be some case you run into where I'm wrong. But generally speaking, yeah, you can run these in any order. The other thing you can do is run individual commands, right? If I don't want to make all, I just want to make main, I can type that. It tells me main is up to date, but that's fine. If it wasn't, then it would recompile it for me. All is just, if I have multiple executables, I list them. Oops. And then when I run make or make all, it's going to say, oh, generate this executable, also generate this executable, also generate this executable. So assuming that I have like commands to do this, if I didn't have the all command, I would have to run like make main and then make main 2 and then make main 3. Whereas now I just have to run make and it'll do everything for me. All right. Other questions? Okay. I guess one last, somebody did bring up header files and I did cover this last class, so I'll cover it here. This is not generally how we handle this. How we handle this is usually if I have a library or a class, there is a source file, but there is also what's called a header file, foo.h. And what that is foo.h has all my function and class declarations, right? So my library consists of maybe some, preprocessor constants and functions and classes. In the header file, I just put the definitions. And then here I can just say, instead of listing every function individually, I just say include the header file. And this has all the functions. And then this should work exactly the same, actually. Make clean and main. So yeah, that's the pattern that we generally use. Yep.
Running our submitted Makefile, or does it have a note?
It depends on the assignment. Yeah, yeah. So sometimes, because yeah, I try to, if there's an obvious way to like sort of make your job easier, then I will run my own Makefile. If not, then I just usually use yours. And yeah, if you're wondering, are there hacks for the tutorials? Yes, there are. Obviously, I can't catch everything. If I do see that you've hacked your way to a better grade than you deserve, then probably there'll be some form of punishment. So generally speaking, I rely on that rather than like really tight scripts to double check everything that you might possibly do. But yeah, you may stumble upon something where it's like, oh, I submitted this and I got full marks and I didn't really do anything. It happens. I would suggest completing it anyway. Yeah. If you find a good hack, please let me know. That's yes. So in this instance, so the question is, do we ever include the .h files in the Makefile? What is happening? Yeah, okay. Yes. Yeah, I should, right? So main.cc, if this changes, I really should recompile this. So that would be a good thing to list here. And yeah, and that can get kind of like complicated, right? Now I have to list basically all the header files as dependencies. That's somewhere where this can break down. Yeah. Yeah, it's just the declaration. So this is a very simple example, but maybe I have multiple functions, like this is a library for doing whatever. And so I might have a bunch of different related functions, and I just list all of the declarations here, and then I include that here, and then I can still compile them separately. Yep. What's that? Which declarations? Yeah, generally only declarations, preprocessor constants, class definitions, things like that. I mean, there's not, again, the goal is to compile these separately. So if you're including a lot of source code in your header file, you include a little bit, but if you include a lot, then that's defeating the purpose. But there are like a header, there are what are called, getting a little bit ahead of myself here, but there are header only libraries that do not have source files. They just put everything in the header. Generally, these are simple and they compile like very quickly. So you might stumble across stuff like that. Then you don't have to link. You just compile everything from scratch. Other questions?
Yeah, for the header. So we have to include the header files always explicitly with the files that includes the header file. Is that correct?
Oh, I'm not sure I understand, but like included here? Include the header
In the
file?
make file, sorry. In the make file, do we have
Yeah.
to always write out header file explicitly always in the line that with the CC file that includes header file?
Yes. That's that is the best way to do it.
Or should we write it with the foo, like foo.h? With whom does it go? With main.cc or with foo.cc?
Where does this go? Like, should it go with foo.cc? It should
Exactly.
also
Should
go
it
with
go?
foo.cc.
Okay, it goes with both foo.cc and main that included it as well.
Exactly, yeah. So if I have a header
Okay.
file, so typically also what I would do, right, is I would, generally speaking, oops. This will make more sense when we get to classes, but I would also include the header file here. Because there might be, especially with classes, right, there's variables defined in the header file that I might want to use here, or there might be a namespace. So here,
Thank you.
this
Makes
is,
sense. So makes sense. So we'll include it everywhere.
yeah. So yeah. So for those of you who didn't hear the entire conversation, the question is, where do we put this foo.h in the make file? And basically anywhere where you include, right? So main.cc includes foo.h. So you should put foo.h as a dependency. Because if you think about it, right, if foo.h changes, I really want to recompile this. Because if I don't, then it's not going to match the object code. Again, we're getting a little bit ahead of ourselves. This will hopefully make a lot more sense when we get to classes, but that's a general rule of thumb. Now, if you forget to include the header file here, you're not going to lose marks. We're not going to be that strict about Makefiles, at least not this semester. Someday, maybe. But yeah, so if you have, as long as, if I run a make clean and then a make all and your thing builds properly, that's sufficient for full marks, right? If you mix up some dependencies, we're not gonna penalize you for that. Right, other questions? Okay. Goodness.
But it's interesting, like main wouldn't notice if foo.h was changed, even though it says include foo.h.
Yeah, yeah. Because it doesn't, yes. Because make is not a compiler technically. Yeah, so a compiler would notice that, well, compilers aren't built to notice stuff like this, but a compiler, it's going to read this file. But Makefiles just they just basically check the last time this was touched, right? So if foo.h was touched since the last time I compiled this, then I recompile it, irrespective of how it is actually related to these other files. Okay. Cool. All right. So that brings us to, let me see if I can Sorry, 1 second. I like this. I like the questions. But this, this class, the problem is when one class asks a lot of questions and the other classes don't ask any, then the one class gets behind. So I'm gonna go a little quickly here. If you have questions, feel free to ask. This is basically, in some sense, supplementary. Like you should know, I'm going to show you a little bit about how the CPU works and how the memory is organized. All right, because this C++ is a low-level language, and it's useful to know these things. Of those two things, though, the memory is what is most important. The CPU stuff you will find useful in building your mental model of computation. But we're not going to mark you on it explicitly. No, it's great. No, it really, it makes everything more interesting. So I'm not, sorry, that's not a complaint. I'm just saying I'm going to move a little fast here. So we're going to talk about CPU architecture, and then we're going to talk about memory layout. Again, the memory layout is sort of the thing that is worth the marks, as opposed to, this is just for your own benefit. So a CPU would look something like this. They're really quite simple, eh? You can actually build a CPU. So a control unit, this is going to decide which instruction gets executed next. A logic math unit, so I could do like a comparison, right? Is this equal to this? Or I can add two numbers together, or a bunch of other stuff. And then there's registers, which are just little pieces of memory that are right on your CPU, right? So typically, let's say I wanted to add two numbers together. I grab them from RAM, I load them into registers, I send them through the math unit, and then the result is written back to the register, and then I write that register back into RAM. And that's how I would add two numbers. And really that's, I mean, I forget what so I'm gonna tell you something that is mostly true probably, but you can build a CPU, all you really need is an increment and a comparison. And I think that's it. If that's not it, then it's not much more than that, right? So if I have some math unit that takes a number and increments it by 1, and I have another math unit that takes two registers and compares them to see if they're equal, then I can build everything else in software. I can build, I can make ChatGPT with that CPU. Technically, it's going to run really slow, but that's all you really need. So CPUs are actually, in terms of what you need, are quite simple. Modern CPUs, of course, they do a lot more than that to make things faster. All right. So what we're going to do is, well, let's see. I'm going to jump ahead a little bit. I'm going to show you essentially, so we talk about compilation a lot, and I'm going to show you what compilation is with a very simple example. So let's say we take this piece of code, and let's assume it's in a main function, and we compile it, right? So there's a bunch of context that we're stripping away and we're not really worried about. But I compile this, and what I get back are a bunch of machine instructions on disk, but when I try and run it, then it loads it into RAM. And those machine instructions, well, if you pick up an assembly book and look at that instruction and look at what assembly it corresponds to, you will see something like this, right? Or if you have an assembler takes machine language and basically translates it into assembly language. So assembly language, machine language are in some sense a one-to-one correspondence-ish, right? So this compiles into this in assembly. All right, questions so far? Okay, so what happens when we run that? Well, let's see. So we're going to look at this simplified version of a CPU. We have 3 registers. We have an instruction pointer that points to the location of the next instruction I want to execute. We have an instruction register. So when I execute an instruction, well, I first have to load it into the CPU. and then it goes off, it gets decoded. And what that means is that, like, you know, the first 4 bits might go into one section, and then the next 8 bits might go over here. The first 4 bits, you know, are going to say like, oh, this is a math instruction, or it's a branching instruction, or something. And then based on that, it's going to use the rest of it correctly. And then the accumulator is just a general purpose register. We're going to just add a bunch of stuff together. And what we are describing is called the fetch, decode, execute cycle. And these are basically how your CPUs work. So to begin with, right, I've compiled my program and then I run it. And when I run it, it gets loaded into RAM, and here it is. And also there are the X and Y variables are stored here on the stack. Okay, so let's run this. Well, the instruction pointer starts at 0. So the first thing it does is it loads the instruction at location 0 into the instruction register. All right, so now we have load 6 in the instruction register. The next step is a decode. And so what that means is that, well, it flows into the CPU and then does what it does. At a high level, we can pretend, you know, we're going to pretend that the CPU reads this and says, oh, I have to go to location 6 in RAM, load the value there, and put it in the accumulator. Okay. So decode, it figures out that it has to do that. Execute, it goes ahead and does that, right? It sends a command out on the address bus, reads this value back into the accumulator, or not the address bus, but the bus. Okay, and then we go to the next instruction. So the instruction pointer now points at location 1. That instruction says add 7. 7 in this case, right? So this is, in assembly, there's, I think it's called direct addressing and indirect addressing, which is in some sense the difference between a variable and a pointer. So when I say add 7, I don't mean add the value 7. I mean, go to location 7 and grab that value. So this is indirect addressing. But first, I'm going to load that into the instruction register. And then I'm going to decode it, which says, oh, go to location 7, grab that value, add it to the accumulator. So in the execute, I do that, and now the accumulator has value 2. The instruction pointer is incremented. The next instruction says store 6. I read that into the instruction register. I decode it. When I decode it, I realize I have to write to this location. So I'm going to grab the value from the accumulator and write it out to here. And there we go. Instruction pointer and program counter. I'm trying to remember what a program counter. I can't. I think so, but I'm not 100% sure. Sorry. I think so. I can't even remember the context that you would use program counter in, actually, but I can look that up later. But for now, yeah, instruction pointer just points to the next instruction. Okay, so I've stored 6. So that means I've stored the value in the accumulator into location 6, and then I reach this that says jump 1. I read that instruction in, I decode it, and when I decode it, it says, oh, now you have to change this value, right? So I'm going to change the instruction pointer to point to location 1. So on the execute step, I change the instruction pointer to point to 1. Then I would guess they are the same thing. But yeah, sorry, I can't remember that word in context. It sounds like it would be the same thing. All right, so that's it. So then I just continue doing that and I loop forever, right? So I'm taking the value in X and I'm adding it to Y, and I'm doing that forever and ever. And that's essentially how your CPU works. So that's kind of slow and onerous, right? But this operates at about 1 billion instructions per second. So while this seems kind of slow, it actually ends up being quite fast as far as we're concerned. Interestingly enough, this assembly, that used to be what we had to program in, right? So that was actually a big step forward from punch cards, is that you can have an assembler where each machine instruction had a corresponding like little string that reminds you of what it does. And so you would write programs like this, and this was like a big pain. And in fact, sort of the moment we went from assembly to like a compiled language like C or Pascal was a huge step in programming, right? Not unlike the one we're undergoing right now with large language models. So really this sort of advancement in the speed of programming, this is not the first time it's happened. It used to be a real pain to do this. So on the Commodore 64, which I started programming on, any good game was written in assembly, which is like kind of crazy to think about. In fact, goodness gracious. So you would get, this is how old I am. So I had it in my Commodore 64, I loved that thing. And we get these magazines, these gaming magazines, and it didn't come with a game, but what it came with was like machine instructions written in hexadecimal. So these are just like, it would just be pages and pages of numbers. And you would have to write those into memory manually, right? So you typed it all out. And if you didn't make any mistakes, which you obviously made lots of mistakes, but then you would have that game for your computer, which was, yeah. So things used to be a lot harder. Now you just say like, oh, build me Tetris, and ChatGPT will do it for you. All right, questions? All right, well, there's some stuff. I'm not going to talk anymore about assembly, but if you're interested, there's lots of, emulators. So there's this, there's a link here for an 8-bit assembler that can kind of like walk you through what it used to be like to program. You can also download an assembler in Linux, probably, or Windows, I imagine. And write assembly right on your computer. All right. So that's how your CPU works. The important part is how the memory works around that. So when we run a program, the operating system allocates 4 areas of memory: the function call stack, the data segment, the code segment, and the heap. So, right, yeah, let's just jump right into it. So remember all those assembly instructions we saw? Those go in the code segment, and that would be right here. So the first thing that executes is this jump 17, and 17 is where our code begins, right? So in between the code and the beginning of the memory is the data segment. And this contains global variables, static variables, and string literals, right? So if I say S equals Bob somewhere in my program, Bob is a string literal, and so somewhere in the data segment, you will see the string Bob, and then probably a terminating character there. Right? So every time you use a string literal, it exists forever in your program, which is, kind of the most efficient way to do it. A short word about this model. This is a model. Now, no model is 100% correct. Okay, so, but this is a useful way of thinking about things that will help you like make programming decisions. And the reason I say that it's not reliable is because, well, C++ is not, you think of it as a language, but it's really a specification for a language, right? And so what that means is that some big group of people get together and decide, well, if I run this command, this should happen, right? And if I run this command, this should happen. And if I combine these 2 commands, then maybe this is undefined behavior, right? So they decide, they make all these decisions. And when you write a compiler, you read the specification and you implement it as best you can, and you make decisions. You basically do whatever you want, as long as it follows the specification. All right, so when I say this is a model, depending on the compiler, it may or may not do this, but this is still a useful way to think of things. Okay. Down here, we have the function call stack. So generally speaking, it starts at the bottom and go away. And then as I make function calls, it adds more and more information to the function call stack. So the function call stack kind of grows upwards until it meets the code segment, at which point you get a stack overflow and your program crashes. Right, so you have limited stack space. If you took 1406 and used Mark Lanthier's notes, which are great, by the way, I love them. So this is not a critique. And also, I just think they're a little bit out of date. So what they would show is the heap here. Right, so the heap grows this way and the stack grows this way. And when they meet, then you run out of memory. I don't believe that is quite accurate anymore. But like I said, it's just a model. Both of these are just models. So neither of them is completely accurate. However, I do know for a fact that it's easy to blow your stack, right? It's easy to overflow the stack. I can just allocate a huge array on it, and my program will crash for sure. Whereas if I allocate that array on the heap, everything's fine, right? So the heap, I don't like this model because I don't think it's realistic. The heap can store a lot more than your stack, which means I prefer this model. So what happens is I say, give me a new student, and the compiler asks the operating system, oh, please give me enough memory to store this student. And the operating system comes back with this piece of memory and then returns a pointer, which is a memory address that points to here. And so I store that memory address on the stack, and then I can use that heap memory to store my student and see what marks they got and do all that sort of stuff. So again, it's a model, and so actual results may vary, but at the time where this sort of thing was used, you don't really know where the beginning of the program is, right? So the question is, why jump 17? Why do we start with that? Well, you could like put the code segment before the data segment. For some reason, they didn't. I'm not sure why. But then the problem is I start a program. I don't know how big this data segment is. So I don't know where the code starts. So I put an instruction here that jumps to the beginning of the code. That's all. There are other ways, of course, you could handle that. Like I said, this is a model, not meant to be 100% accurate, but useful to think of things this way. Okay. All right, data segment, global variables, static variables, literals, code segment, program instructions, function addresses, function call stack. Every time you make a function call, it takes all the local variables and parameters and puts them on the function call stack along with some other stuff. So that's nice, easy, quick memory. And then the heap is like return from systems call. It's not as fast, but it is persistent, right? That means that every time I return from a function call, I lose all that memory. Any variables there are destroyed. My heap is there until I tell it to go away, right? Until I tell it to delete itself. So it's useful in that way. All right, questions? Okay, so this memory model is, again, the more important part. It's a part for marks. Because as we talk about C++, we're going to talk a lot about the stack and the heap, which are the two pieces of memory that we are the most concerned with as programmers. Before we do that, we're going to talk about basic language features. I feel like maybe I'll write a woo clap for next week. This is sort of a little bit dry. And it's a bit of a repetition, so we're going to talk about things like expressions and statements and what's the difference, and probably maybe a lot of you already know. And however, the one semester where I decided we don't need this, I'm going to skip it. I got a lot of questions, like a surprising number of questions about, whoa, wait, what's happening here? And so I keep it in. For those of you who are very good programmers, this is going to be a little boring, and I apologize. If you find it useful though, great. Let's skip. I'll try and go fast. We're gonna have to go fast because we are falling behind. All right, so just a short history, right? So assembly was one of the first things we programmed in. And then we found some other languages, right? If you're a COBOL, if you know COBOL, you can make a lot of money working for banks. But basically, C was 1972 and C++ was 1980. These are very old languages, but they've been evolving. But there is a lot of legacy stuff in C++ that you'll see, which is like, it's weird, right? But it's because it's old. And we didn't know all the things that we know now. But in terms of languages, what's the difference? Like, which is the most powerful language? Well, that's not really a statement that makes sense. They all have the same power. They're all what is called Turing complete. Alan Turing, by the way, if you're interested in computer science history, it's a very interesting character. If we have time, maybe we'll talk about him sometime. But so Turing complete, which means that if I could solve a problem in one language, I could solve the problem in another language. One language might be faster, but the set of problems that I can solve is all the same. So what is the difference? Well, usually speed and convenience, right? So you trade, C++ is fast, but it's complicated. Or I can trade all the complexity and away in Python, and Python handles memory and all this other stuff, and everything is abstracted away into a list, and writing code is really easy in Python. Right? But in terms of what problems they can solve, they're exactly the same. So all programming languages run on data. What types of data are there? Well, there's really only two types of data. There's ints and there's floats, right? There's floating point. There's you can do other things, but in terms of what we use, you have ints and floats. You have signed and unsigned and things like that. And you have different sizes, right? You have double precision floats. Or I have a char. Well, that's just a 8-bit int that if I try to write to a string, I look up in a table which character I should draw to the screen. But a char is just an int. A bool is just 8 bits to represent a 0 or a 1. So you have floats and you have ints. But we can put those together into aggregate data types, so classes or structs. These are just basically a bunch of other data types pushed together in memory and treated as a single unit. We can also have memory addresses, right? So if I write something like this, stu will contain a memory address to this student. All memory looks the same when we look at it, right? It's just a bunch of ones and zeros. I cannot tell if this is a double or an int or whatever. It's not a char because it's more than 8 bits, but how does the compiler know? Well, when it looks at it through the lens of a variable, and the variable has a type, and the type tells it how to interpret it. Right? So int, double, char, these are different types, and it tells the compiler how to treat it. All right, in C++, we manage our own memory, and there's two main places that we're concerned with, right? So we don't really worry about the data segment or the code segment. We just worry about the function call stack and the heap, right? So a lot of the stuff is abstracted away. When I started programming on a Commodore 64, basically you had a bunch of memory. It's 64 kilobytes of memory of RAM, right? And then you had some extra memory locations for, like, say, the screen. If I wanted to write a pixel to a screen, I would write a 1 into a certain memory location. But other than that, you had to manage everything yourself, right? You could just, where do you put your code? Well, wherever you want. or just write it wherever. And then when you want to run it, you make a sys call with a memory address, and which says, start running the program here and just grab everything and interpret it as a machine language instruction. So we've moved away from like that sort of cowboy Wild West of programming. Everything is sort of, there's a lot of organization done for us, which means that function call stack and the heap are sort of two fundamentally different things that we have to account for. The function call stack, every time I make a function call, I put a new stack frame down. That stack frame contains local variables and or parameters and maybe some other metadata. So from main function, I call foo, another stack frame goes on. From foo, I call foo2, another stack frame goes on. Foo2 allocates an integer and then returns. When it returns, I have a function pointer and I move it down to the beginning of the end of the previous stack frame. And so what that is I'm in essence popping this frame off the stack. I don't delete it or anything. Well, I call the destructors on whatever's there, but and then what happens is next time I call a function, it gets overwritten, right? So the stack kind of grows up and down as I make function calls and return from them. And if I allocate local variables there, they're very quick to, I have quick access to them, and they get deleted for me. So when I draw a stack, I'm going to sort of draw like a bunch of cubes on top of each other. When I draw the heap, I'm going to draw it as a blob like this because it's less organized. And the reason why it's less organized is it starts out pretty organized, but then when I start deleting stuff, right? So maybe I allocate a bunch of ints here and they're all in a row and that's nice and easy to find. But then I delete one. And now I have this space of 32 bits and the heap there's a data structure that keeps track of all of this stuff. So that means the heap is slower. When I ask for memory, right? If I ask for a new int, it's got to look and see if it has any holes that it can fill, essentially. And so, but the nice thing is it stays in memory until I call delete. So there's two ways to declare variables in C++. For the first assignment, we are sticking with statically allocated, right? So you don't use new. I don't know if I'll have to decide whether that's a hard and fast rule. I think I'm going to make it a rule not to use new for assignment 1. So we're going to learn about the stack in assignment 1. So basically, anytime I allocate a variable and I don't use the word new, that's statically allocated, right? And it's just like this. I just declare the type and the variable name. Over here, if I use the word new, well, that's going to return a pointer. So right away, I have to store that in a pointer. So there's a lot of different syntax, but the way that you can tell, is this dynamically allocated or statically allocated, is dynamically allocated always uses the word new. If you see new, that's on the heap. If you don't see new, that's statically allocated, which means it's going to be allocated within the current context. All right, we'll stop there today. Next class, there will be a woo clap, and then I will get your assignment and your tutorials out hopefully today. If not today, then early tomorrow. Yeah, I really like the questions. It's just the other two classes are at 8:30 in the morning and nobody asks questions. So feel free to ask questions. I'll manage. Yeah.
So how are you?
Good. How are you?
Good. I'm just curious how you got the code up because when I tried it doesn't work for me.
You got the what?
The introduction code on your VS. I tried to do it my side and you get an error. I'm thinking I'm doing something wrong, but
Oh, maybe I mean, there might be an error in it. Include IOStream. Oh, are you on Windows?
you know, when I was
And what are you using? Like, are you just compiling on Windows?
just trying to do what you didn't code like.
But by default, it doesn't have the GCC compiler installed, eh? Windows?
Okay, so I have to install myself. Right?
You can install it yourself. Yeah, that'll work. Or you can use, I'm using Windows Subsystem for Linux. That's very, I would recommend that actually. So you just go to the Windows Store and look for Ubuntu. It's free. Yeah, so that one or that one. Yeah, those are both fine. And then there might, you might have to turn on the hypervisor or something, but it gives you, it's pretty good about giving you instructions how to do it.
Okay, awesome.
Yeah, great. All right.
I have two questions.
Yeah.
Like, so I was in 2401 last semester.